Then it's exercise 3, homework 5. So we will here use the simulations to understand the behavior of the estimator we found in the previous exercise. Remember, the estimator was beta n hat equal the sum of the xi's times yi's divided on the sum of the xi squared. We will take, so first a little information. We will take epsilon 1, epsilon 2 and epsilon n to have a normal distribution. A normally distributed variable x with expectation mu and variance sigma n has following distribution function, probability distribution function, which you may have seen earlier. F by x is equal 1 divided on the square root of 2 pi times sigma times e in the power of minus x minus mu in the power of 2 divided on 2 sigma in the power of 2. So we will use all this through the exercise. And I also ask you to remember that this we found that was this sigma hat in the power 2 on this form is an estimator for sigma in the power 2, and beta n hat with this formula is an estimator for beta. And remember, sigma in the power 2 and beta was the unknown parameters in the model. So therefore we have estimators to estimate these parameters. Okay, this is mostly Python everything. So first of all, we are asked to look at the code and understand these lines from 35 to 40. So first we make 100 data points here. We set that the beta, the real beta, the known beta is 4.56 and the sigma 2 is 2.34. So if I go here now, this sigma 2 is this one and the beta is this one. So we know these parameters. X is equal, we just let x be an array here between 0 and 1, split it in 100. So 0.01, 0.02, 0.1, 0.11, 0.12, 0.99 and 1 probably. So there's the x values, and then we draw here 100, n is 100, random normal numbers which have mu 0 and standard deviation squared sigma 2. So that's the square root of this 2.34. So here we draw the epsilons and we draw 100 of them. And then we make the y's. We know that the y's is the x's times beta plus this randomness epsilon. And we get 100 y's because x is 100 elements in x and it's 100 elements in x. And this beta is just multiplied into the x array, and it's multiplied with each of the x's. Okay, so here we have the y's. Then we can actually calculate the beta hat. And how do we do that? Yeah, we use the estimator here. And then we get a number for beta hat, which is an estimate for this beta. So here I do that, just fill in on the formula, sum of the y times x divided on the sum of x squared. So let's run everything here. And we see that we get 4.44. We should get 4.56 almost. We know that the right beta is 4.56, but because of this randomness, these epsilons, which has an expectation of 0, anyway makes it make this beta hat not to be exactly beta, but somewhere around. We have some variance here. If I now run this once more, we will see that it changed. It's not 4.56 or 4.44 anymore. It's it's 4.579, because now it has drawn new 100 randomly numbers from this standard normal from this normal distribution, I mean. Okay, and we could do this a lot of times, and actually let us do that, and that's what we are asked to do in so now we have done A and we have done B. Okay, let's run this code once more then, so we really have done B. And now we got 4.05. That was actually a pretty special, pretty long away from the real beta 4.56. Maybe not so long actually. So, but how can we do this a lot of times and store these beta hats? We can do it with a for loop, and that is what we are asked to do in C. So we are actually doing exactly the same as in A, but we are making a lot of these beta hats, and then I need a for loop. So first of all, n equal 100 as in A and B, beta the same, sigma 2 the same, x the same. But now I want to make 1000, 10 in the power of 3, 1000 beta hats. So wanna make 1000 beta hats. And then I have to make an array or vector, or what you want to call it, of beta hats. And I will fill this up with 1000 beta hats. So, and that I do with this for loop. So I go in between 0 and 1000. And every time I go into the for loop, I draw 100 randomly normal distributed numbers, and they are actually distributed with expectation 0, because epsilon have an expectation of 0, and standard deviation squared root of sigma 2, because that is the standard deviation of the epsilons. If you look in the text, for example, in exercise 2 or 1. So y is, and then we make the y's, which is just x times the beta plus epsilon, just as in 3a. And then I make the beta hat in the same way, that the sum of y times x divided on the sum of the x in the power of 2. And then I put this beta hat into the vector beta hats. So now the first element of beta hats is this first calculated beta hat. And when I now go in the for loop for second time, I draw new 100 epsilons. I make new 100 y's, and then I calculate a new beta hat, and then I put this beta hat into beta hats vector, and this beta hat will be the element 2 in beta hats. And then I go into the for loop for third time. I draw 100 epsilons. I make new 100 y's. I make one new beta hat by taking the sum of the y times the x divided on the sum of the x in the power of 2. And then I put this beta hat into the vector beta hats, and then this time it will be the element 3. and we do this 1,000 times, so we get 1,000 elements in beta hats. So that's what exercise 3C is all about. And then in D, we are asked to compute the empirical mean and variance of the 1,000 estimates of beta. So now I have 1,000 estimates, you know. So then I take the mean to these beta hats. So that's the mean of 1,000 beta hats. Let's see what it is. First of all, we have to run this. And then we could calculate the mean. And what should this be pretty alike? It should be pretty like 4.56, because beta hats is just an estimate of this beta, and we have now 1,000 estimates, and in the long run the mean of these will be beta, because that we have showed earlier in exercise 2. Actually in 2E. F. So and let's find out what it is, and then we could run this, and we see I got 4.549. That's very close to 4.56. And if I did, and then I can find the variance of the betas. Then I get .074. But and this should be close to the theoretical variance. And the theoretical variance is for beta, remember, the theoretical variance for beta, and let's find it. It's somewhere here. This is the theoretical variance. Here, variance beta n hat. We did that in F. Here is the theoretical variance. So let's calculate it. So here I calculate the real sigma beta. That is 2.34 divided on the sum of the x in the power of 2. And if I run that one and run this one, I will get I will get 0.06984. I get this number. That's the same every time. But this is simulations mean beta and simulations var beta. They will be different from time to time, from every time I do this follow-up. If I now do a new follow-up, I will get new sim mean beta and new sim var beta, but they will be very close to the theoretical parts. And that's the point. Okay. Then we can do the last exercise. And that is E. Here is a fact of our model. When, let's see, when epsilon 1, epsilon 2, epsilon n all have a normal distribution, then the estimator, so here when epsilon 1, epsilon n all have a normal distribution, then the estimator beta n hat also has a normal distribution. And this normal distribution is actually this one. Why is it this one? Because the expectation of beta n hat is beta. We showed that in exercise 2F. And this is the variance of the beta n hat, which we also showed in exercise 2F. And since I now have the expectation and variance on beta n hat, and I know that beta n hat is normal distributed, I know what the normal distribution is, that is this. So by us, we got now 4.56 as beta, and sigma in the power of 2 is 2.34. And then I have, on this sum of the xi squared, we also know what that is, but I haven't calculated it here, but we could put a number here too. So now we are going to make a histogram of all the beta hats, and then plot the density curve of this normal distribution onto that histogram, and we will see the connection. So here I define the normal the PDF, probability density function of this normal distribution, and we know that that is 1 divided on the squared root of 2 pi times sigma beta, which is this one, and times e in the power of minus x minus beta in the power of 2 divided on 2 times sigma beta. And so then I run this, then I have defined this function, and then I know that this beta hats has expectation beta, which is 4.56, and I know that I will get results when I estimate beta on both sides of 4.56, but not so very far away from 4.56. So I actually choose to say that I want to make this density curve between betas for 3 to 6. So that's what I'm doing here. So that I run. And then I just plot the histogram of all these 1000 beta hats, which I have in this vector here. And I plot the density curve up on that. So let's see what we get. We have to run some more here, I think. Here. So here you see the histogram, and we can see that the density curve really fits this histogram, this density histogram. And that is because we know, or we can show mathematically, that these beta hats, they are actually normal distributed, almost normal distributed. If this n get high enough and I make enough simulations, I can make this histogram to just to perfectly fit this curve. Yes. So the area under this red line is 1, and the area under the blue is 1. So the conclusion is that we can see that the histogram fits pretty well the density curve of the related normal distribution for beta hat.